Happy Thursday, everybody. I really hope that you are looking forward to the Headmaster's holiday tomorrow. I certainly am, and so this will be the last video of the week. And so today we're going to talk about two things. I want to kind of review with you the cell line notations, what are also known as cell diagrams, because you just read about them yesterday. And then also we're going to look at the relationship between E cell and delta G. And so in this case here, right, to talk about cell diagrams, we see that we have our zinc copper cell again. And just to kind of refresh our memory, we're going to look at over here at the E-reds for each of these. And we see that with the E-reds, since the copper E-red is more positive, then that is going to be the cathode, right? So the copper will be at the cathode end, and since the zinc is more negative, this means that this is going to be at the anode end. And so again, just like you read yesterday, if I'm going to write a line notation for the cell to kind of make it easier, what I'm going to do is start with my anode, and I'm going to start with the electrode. So whatever the electrode is, I'm going to start with on the in the anode. I'm going to start with on the left hand side. So that is going to be my zinc, and my zinc is a solid. And then I'm going to draw a line. And so anytime that I change states with something in that cell, I draw a line. And so in this case here, I went from a solid, and the next thing I have is my Zn2 plus, which is in solution, right? So those are the two things that are at the anode end. Then I can draw two lines, and that two line represents my salt bridge. So that's kind of that salt bridge connecting my two cells together. And then I get to my cathode. And when I get to my cathode, again, I want to put the electrode on the outside. So whatever substance represents the electrode, it's going to go on the outside. And so then I'm going to start with my Cu2 plus, what's in solution. Then again, I have a change in state because I'm going from my aqueous state, and then I have my Cu as a solid. And so this right here would be my line notation or my cell diagram for that particular cell. Pretty simple, pretty straightforward. Okay, now let's look at what happens if now my cell is a little bit different. And so this is a cell that we looked at before. It's the hydrogen cell. And again, right, we can look at our standard reduction potentials. We see hydrogen has a standard reduction potential of 0. And then we see that copper is 0.34. Again, copper is more positive, so it's going to be at the cathode, which would put my hydrogen at my anode. Now again, with this, now we have something a little bit different because we have hydrogen as a gas, we have our H plus ions in solution, and we also have our platinum electrode. And so that's taking place at the anode. So again, we're going to start with what the electrode is. My electrode's made up of platinum, so I'm going to put my PT here as a solid, and then I'm going through a state change, and so I'm going to have my line, and then the next thing I'm going to have is my hydrogen, H2, that's getting pumped in, and that's a gas. But now I have another state change, and so whatever comes in solution is going to come last. And so in this case here, I'm going to have H plus. Now I have my salt bridge again, double line, right? That represents my salt bridge. And then I'm going to do what's in solution, Cu2 plus, right? So that's aqueous. And then my line, because I have a state change, and then Cu, and that would be my solid. So this whole thing here would represent my cell diagram or my line notation, right? And remember, on this side we have my anode, and on this side we have my cathode. And these are good because then you don't have to draw the big cell like we do up here. We can just have this line notation. And what we do, if we don't sell anything, we could actually put in concentrations here. So we could have 1.0 molar this, and let's say we change that to 0.25 molar. So that would look a little bit different, in which I could say, okay, in this case here it would be PT as a solid, line H2, line 0.25 molar H plus aqueous, boom, boom, and then 1.0 molar Cu2 plus aqueous, line Cu. Now, if you don't see concentrations, that's implied that it's going to be 1 molar. this will become important to us here on Monday when we start talking about cells that are in the non-standard state. All right, so, but before we get there, let's talk about the relationship between cell potentials and Gibbs free energy, okay? And so a couple things that we already know when we look at this. We learned earlier in this unit that when E cell is positive, that means that that reaction is happening spontaneously. That means that, hey, the substance with the higher potential, right, or the E's more that can be more easily oxidized is at the anode. It's going to flow spontaneously over to the thing that can be more easily reduced, and so we know that that's going to happen. So that means that E cell is positive, and that would happen spontaneously. And we know how to calculate E cell now. We also know when delta G is negative, right, in terms of a chemical reaction, that also means that it's spontaneous, right? And so because of that, there has to be some relationship between E cell and delta G. And fortunately, someone very smart figured out the mathematical formula that would help us relate those two values together. And so if we know what E cell is, we can very easily calculate delta G for that process, right? And likewise, if we know what delta G is, we can very easily calculate what E cell would be for that process. And so the two things are related through this formula that we see here, right? We see delta G equals negative NF E naught cell. And so it's a really simple equation. Now, N and F, and we know from PV equals nRT represents the number of moles, but in this case, it's going to be the number of moles of electrons transferred during the balanced redox reaction. So if I kind of go back up, we'll get to there in a second. And then F right there is something known as Faraday's constant. And basically, it is just the charge on 1 mole of electrons. So if I have 1 mole of electrons, the charge of that in coulombs is 96,500. So that's all Faraday's constant is. It is the charge of 1 mole of electrons. And so now, again, remember we see here, and this is very important to remember. So if I have the number of moles, then I have my Faraday's constant, which again is in coulombs per mole, and then my E cell is in volts. Well, you're looking at that and how's that possible? Well, remember earlier in the unit we said that a volt is a joule per coulomb, and so now if I look, my coulombs would cancel, and leaving me with my delta G according to this equation is going to be in joules. And so when we calculate this, delta G would be in joules, not kilojoules, so we would have to convert it if we want to use it with delta H, for instance. So how can we calculate what delta G would be for our zinc copper cell, right? And so again, remember we have this over here, and we now know that copper is at our anode, so we know that's 0.34 volts. We know zinc here is negative 0.76. We know now that E naught cell is going to be equal to the E of the cathode minus E of the anode. And so that's going to be equal to 0.34 minus a negative 0.76. And that's going to give us our 1.10 volts. Now, so that's good. We already know, hey, we have E cell, right? So we know that now delta G is going to be equal to negative NF E naught cell. Okay, so the question is what is that number? So if we look up here, right, we know that we have our Cu2 plus 2 electrons. That is going to get, sorry, there should be an arrow there. That is going to go to my copper as a solid. Then I know that my zinc is being oxidized, so I have to flip this reaction here. So that's going to give me Zn going to Zn2 plus 2 electrons. Now if I look, right, I don't have to multiply them by anything because top one has 2, bottom one has 2. Those 2 would cancel out. So when I add these together, I'm going to get Zn plus Cu2 plus going to Zn2 plus Cu. And so the n that I would use over here would be, in this case, n equals 2 because that's what I had to cancel out there. So if I go back here and I look, now I'm going to say, well, delta G naught equals -2 because that's what I canceled over there, times my 96,500 times my 1.10. And so if I do that, I'm going to get a negative 212,300, and again that's going to be in joule, right? So then most of the time we're going to convert that, so that would be a negative 212.3 kilojoules. And you can see because of this, right? Anytime that E cell is positive, because of that negative sign there, this is going to end up being negative, right? So if E cell is positive, this answer has to be negative. There's no exceptions for that, right? Because if we look here, that negative there makes it so. Okay, so this is all we're going to do today. I want you to work the book problems that you see in the daily task and make sure that you understand those. If not, reach out via Teams and let me know what you're struggling with. I hope you guys have a wonderful weekend. Make sure that you are taking some time to do something fun. I know it's hard to do now, but just do something fun for yourself, all right? And we'll touch base again on Monday. All right, guys. Peace, love, happiness. Thanks for playing.